Hello, hello. Hope y'all are doing well. I am currently on Kairos retreat doing who knows what, but y'all still need to learn the law of sine, so that's what I'm here for in this little video with the power of modern technology. So we're going to talk about law of sines. You may have seen this before, you may not have. It's actually a very easy formula to use, so I want to show you some motivation. Why do we actually learn this? I'm going to prove it to you using a really simple proof, and then we're going to see how it works out in some example problems. So the first thing that you guys already know how to do is basic sort of SOHCAHTOA and solving for missing sides, right? So if you look at these triangles here, we've got an angle. We've got our opposite side over here. Here's my hypotenuse. If I asked you to solve for y, you'd be able to do it pretty easily, right? You have opposite hypotenuse. If you look at SOHCAHTOA, right, that's the SO part of SOHCAHTOA, right? So that tells you that sine of the angle, 26 degrees, is equal to the opposite, which we're calling y, over 25, right? Opposite over hypotenuse. And so if I wanted to find out y is, I have an equation now that I can solve, right? I can multiply both sides by 25, and I will get this is equal to y. In fact, I can even go further. If I have a calculator and I'm in degree mode, right? I could type in 25 times sine of 26, and I get 10.96, roughly. 10.96. So it's roughly how long the side length of y is. And I could do that for these other two examples. The point is, it really doesn't matter what orientation the triangle has, as long as you can identify your opposite side, your hypotenuse, you can pretty much set up the same equation, right? This will give us sine of 53 degrees is equal to x over 13. And this equation solves in the same way, right? Sine of 53 degrees times 13 is equal to x. And I can just type that into my calculator here. I get about 10.38. 10.38 for x. Kind of sound like the Khan Academy guy. It's weirding me out. I guess that's just what happens in these videos. You know what? Let me change this around. Let's switch the z and the 106, right? What if the 106 was over here and the z was here, right? Well, let's think about the equation we'd get, right? Across from my 62 is the 106. That's my opposite. Here's my hypotenuse. So the equation I get here is sine of 62 is equal to 106 over z, right? So it's slightly different, right? So it's going to solve in a different way, right? When you solve this for z, you should get z equals 106 over sine of 62. And if you don't see how I got that right, just go through those steps very carefully. I didn't show all the steps here, but just solve it like you normally would. You should get that. And again, this is something we could put into our calculator. So this gives me that z is approximately 120.05. Right. So those are just some basic examples with right triangles. But, if you're a very curious person, you might say, well, this only works if you have a right triangle. Is there anything we can do if we don't have a right triangle, right? So, I got these two cases, right? I can easily do this one, right? Here's my opposite, here's my hypotenuse, bada bing, bada boom, I can solve that. What about this one, right? Am I still able to use SOHCAHTOA here if I don't have a right triangle? And the answer is a big old no. Right, so I cannot use SOHCAHTOA in this case. I can use SOHCAHTOA over here because it only works with right triangles. That is the whole thing about SOHCAHTOA. So the question then is, okay, well, what do I do if the triangle is not a right triangle? And so that's what I kind of want to prove to you today. I'm going to do a kind of visual proof here, and it's going to rely on stuff that you guys already know, and we're just going to kind of take it into a whole other level. So let's say we have this triangle here, and let's say it's not a right triangle, right? So this angle up here, let's say that's not a 90-degree angle. I know it looks like it, but let's say it's not. And we want to give names to some of these angles. So let's call this angle A. Let's call this angle B. And let's call the side across from A little a. Right? I actually don't want that arrow there. And let's call the side across from big B little b. All right? Let's give them names that sort of make sense. Is there any sort of relationship I can draw between these angles and the sides? Well, remember, SOHCAHTOA only works on right triangles. And one thing I could do is maybe I could draw a line in this figure in such a way that it creates a right triangle. So what if I drew, this is called an altitude, right? A straight line that goes down that creates a 90-degree angle here and here. Let's say this line segment has length h, little h. You might notice that this new triangle, this new triangle has two right triangles, which if I wanted to use SOHCAHTOA, I could, right? But I'd have to use them on the individual triangles. So let's say I work on this triangle on the left side. Here's my angle, there's my opposite, that's the h, and here's my hypotenuse, right? So if I use SOHCAHTOA on the left triangle, I get that sine of capital A equals h over little b. And if I solve for h, I get that h equals b times sine of A. Okay, so you might be wondering, why is that important? Okay, well, let's see what happens on the other triangle here. Let's use SOHCAHTOA on the other triangle, right? So here's my angle. My opposite is the little h. And my hypotenuse is this little a side. Right? So this one gives me a new equation. Tells me that sine of capital B equals little h over little a. And when I solve it, I get that h equals little a times sine of big B. And look at what we have here. We have this equation and this one, and they both tell us what h equals. All right, so on one hand, we have that b times sine of capital A is equal to h, but on the other hand, we have that h equals a times sine of capital B. And at this point, if you have three expressions that are equal, you can basically get rid of this middleman and just set the two sides equal to each other. Well, if you rearrange this equation, let's divide both sides by a times b. Right? Divide both sides by a times b. You'll notice that this b cancels with this one, this a cancels with this one, and we end up with something really nice, that the sine of capital A over little a equals the sine of capital B over little b. And that right there is essentially a proof of the law of sines. Now you might be wondering, what about this other angle that we have sort of here and this other side, right? We might call this big C. We might call this little c. Do those factor into this law? Well, if you think about it, of course they do, right? So the decision to draw this altitude here was completely arbitrary. We could have drawn it anywhere, right? We could have drawn an altitude like this maybe, right? That could have been an altitude, or we could have drawn an altitude like this. Well, they're supposed to intersect all three altitudes. Let's see if I can get it. Yeah, there we go. Could have drawn the other two altitudes, and that would have created a relationship between A and C or B and C. And so it would give us the same exact relationship, which tells us that sine of capital A over little a is not only equal to sine of big B over little b, it's also equal to sine of big C over little c by the same exact logic and mathematics. So the full law of sines says this. Sine of capital A over little a equals sine of capital B over little b, and it's also equal to sine of capital C over little c. So these sides and their corresponding angles, if you sort of pair them up in this way, right? These opposite sides correspond with their angles. That proportion is essentially constant no matter which pair you choose. And so this is just something we can use that we can now use to help us solve non-right triangles, right? Any triangle, this law works. So it would probably be helpful to go through some examples, right? So let's just start over here. Well, look at your opposite sides, and if it really helps you, right, you can actually just label your sides. Call this capital A and this little a. Call this capital B and this little b, right? And just use the formula exactly the way you see it, right? We know that sine of capital A over little a equals sine of capital B over little b. All right, let's just put all the numbers in. Sine of, it looks like we have 80 degrees over 16 equals sine of 51 degrees over x. And now we have an equation where we can solve for x. And if you do that, right, you could take the reciprocal of both sides. I'm going to save the calculator stuff for the very end, right? So I'll take the reciprocal of both sides. And it looks like now I can multiply by sine of 51 on both sides, so that these cancel. So we're left with that x equals 16 times sine of 51 degrees over sine of 80 degrees. And now, let me go ahead and put this into my calculator. 16 times sine 51 divided by sine of 80. And this gives me an answer of about 12.63. And that is supposedly how long x is, which makes some sense, right? So the side across from the biggest angle should be the longest side. So we should expect a slightly smaller number to represent what the side length of x. All right, let's maybe try to do another one. All right, so over here, we have this angle paired with this side, right? So that tells us that sine of 110 over 61 should be equal to this angle paired with this side, right? So sine of 23 over y. And I might skip over some of the steps just to save time, but it looks like this one's going to solve very similar to the last one, right? If you solve for y, you should end up with 61 times sine of 23 over sine of 110. and you end up with y is approximately 61 times sine 23 over sine 110. It's about 25.36. And again, notice how the side across from a very tiny angle results in a very tiny distance, right? So your answer should make sense if you've done this all right. If we got a side length longer than 61, then we have a problem, right? This side is definitely shorter, for sure. So just use that to sort of check your work. And we also have this side, these two sides paired together, right? So we have sine of 35 degrees over 117. That should be equal to this angle paired with this side. So sine of 85 degrees over z. And if I solve this one, we end up with z equals 117 sine of 85 degrees over sine of 35 degrees. (117) times sine of 85 divided by sine of 35. That gives me around 203.21 as the length of z. And that kind of makes some sense. We had a larger angle there, so we should expect a larger side. Right, so I was going a little quicker because it's very likely you've already seen this before. And so I didn't want to take too much time, but use the rest of class time to just work on the homework, look into law of sines, and if you want to take a sneak peek at what we're going to learn next week, which again is probably something you've already learned, is look into the law of cosines, which is a little bit more complicated of a formula, but it also has a pretty nice proof to it, which I'll probably show you. And that's going to set us up real nice for vectors. So thank you guys for watching. Looks like I'm going to have to cut it off here. Seems like my dog walked off and pooped somewhere, so got to clean that up. But hope you guys have a good weekend, and I'll see you back next week. We'll get started on law of cosines. Anyway, take care. Bye.